Okay, so it says I'm recording. Hopefully this works. It's the office hours. It's not the recitation one, so it's not going to be automatically uploaded to Courseworks, but I'll upload it after the session ends. Okay, so I think we're ready to start. Please let me know if there's any other I'm hoping to make this a little bit more interactive than just me sort of lecturing. Can I also review the WordNet and AMR and how will this part be like? Yep, I can review those things for sure. I was thinking about first going over the things that people sort of asked about on EdSTEM, but I'm hoping to make this a little bit more interactive because I think that would be a sort of the best way to do this to like kind of get the most out of it for everybody. So, please feel free to like shout out questions or put them in the chat as we go, or if like something's not super clear. I'm going to be just sort of going through like I don't know, I'll just be sort of going through the information. And so it's going to be a little bit, if you have a question about like something that's more specific, like feel free to jump into it. But since the three concepts that people asked about, neural networks, backpropagation, and attention, self-attention, are all kind of related in that order, I'm thinking about sort of going through those first. This should be about hopefully not 2 full hours, but that's the time I scheduled for it. And so if that's how long it takes to get through all the questions, like that's great. But maybe we'll get out of here before that. So yeah, let's get started with neural networks. So I guess maybe some like motivation for like maybe a problem that we might look at using neural networks. We might think of like the idea behind a neural network is we can sort of like basically learn any nonlinear or linear function very easily using a neural network and just sort of as a black box figure out some function f that like maps the data that we have whatever format it's in. X maybe is some set of examples that we have. Maybe I'll make this a little bit of a, so maybe we have n examples with n features, and we're trying to map that to some other some sort of like solution. Maybe it's a y that's like in the set of 0, 1. Maybe we're doing binary classification, and there's n of those, or maybe we're trying to map to some other regression real valued pair for n. And so the neural network does is basically it learns this function. And so let's for example take like a linear model, for example. So we might have some, let's look at some like natural language example where we have maybe a few sentences, which is like, let's say like word 1 to word n, and some like maybe positive or negative sentiment. And what we can do here is we can sort of convert these to features, because we can't just sort of like put in a neural network just like straight up text. We have to somehow encode our information sort of digitally, right? And so what we can do here, maybe for example, is we can come up with some feature function that basically takes basically can be like an indicator function for some word. And so for example, maybe if the word if word 3 is in the example, then this is equal to 1. This is an indicator function. So for example, let's say we have an example that is W3, then as we convert, so let's say these are like 2 different examples. If we have like a feature set 1, we can say that this is going to be 1 and this is going to be 0. And so like if we did this for like every word in our vocabulary, we would then have like sort of this array where we had like different words that would be so like we can feed this sort of in as like a so like a classifier model. And so we can introduce the idea of a perceptron, which is sort of this idea that we have this function that we can linearly classify, we can do a linear classification on some example, 1 or 0, if the sum total of the weights are greater than 0. So basically the idea is that we have this function phi, right? And we have I of them, right? I can be in, maybe the vocabulary is V. That's an indicator function over the word I, if it's in the example X, right? So this function is equal to 1 in instances where the word is included in the example, and it's equal to 0 in instances where the word is not included in the example. And we're trying to classify, examples into 0 and 1. And so maybe it's the case that we're trying to classify things into positive and negative sentiment. And so, for words like good, we'd want that to be, if we're trying to classify 1 as positive and 0 as negative, we might want words like good to be, very highly weighted, right? Because a word like good is going to very much signify sort of whether or not that word is, if that word is positive, we want good to sort of be like a high value, right? And a word like bad maybe as a low value. And, a word that's sort of neutral, like the word the, might just be sort of a flat value, right? Because we basically want to multiply this indicator function, these 1s or these 0s, with a weight, which is some, real number, that then if it's greater than or equal to 0, we can classify that example. Does this make sense so far? And so these, and I'm actually going to change my, the way I'm doing this, because the W's, I's might get complicated. This is a word. This is a weight. So we want to assign a weight to each word, basically, just to try to like, classify the example. So like each WI, weight WI indicates strength of, feature phi for any example X. And if the sum total of those weights, positive or negative, are greater than or below 0, we can classify it. So the idea here is that we sort of want to use a neural network to learn these weights. So use neural network to learn weights. Okay. So hopefully this kind of gives some intuition. So this might be 0.9, this might be negative 0.9, this might be 0. So if you have a word, okay. So this is a perceptron. A neural example might be what is phi representing again, the symbol that looks like a Q. This is a function. So this, I'm going to change this. Phi is a function that takes in an example and spits out a feature for the neural network to use. So for example, we might take an example like, good things. And if we put it in this phi, we will get, if we use this phi where, like, let's say, like, for example, the phi is whether or not the word good is in the word or not. That might then be like represented as 1, or if we have like an example that's bad things, that will be represented as 0. So it's a way of translating our example into 1s or 0s, depending on whether or not a word is in the example. Okay. So we want to pump it up a little bit, and now we're going to look at multi-layer perceptrons. So the idea here is that, we have this idea of a perceptron that takes weights and features, and classifies examples into 0 or 1 depending on the weights and the features that are included for any given example. So the nice thing about the perceptron is that we can share weights across the different examples, but each different example can use the same weights to classify an example. So a multi-layer perceptron, which is sort of what you might classically think of as a neural network or a feed-forward neural network, is basically represented pictorially as a directed acyclical graph. And so we might take this input X, let's say that our vocabulary is equal to 3, and that these are all indicator functions over different words, right? So in our previous example, we can think that like, I'm not going to use W1 and W2 and W3. I'm going to actually use good, bad, and I don't know, fish. Okay. So this is basically the input, right? We'll have a bunch of 1s and 0s for each example. Then what we want to do is we have what are called hidden layers, which you can have as many as you want. Let's just put 2 here, for example. And they can be different sizes, right? You can have 2, you can have whatever number in each layer, and then some output layer. We'll just have a single output layer. And the idea of what's called a dense network is that each of the nodes in the previous layer connect to all of the nodes in the future layer. And so, for example, this node is going to connect to every single node in the next example or in the next layer. And that's going to be true for all of the different examples. Okay. So you see there's like kind of a web of these like little lines that I'm drawing here, right? And the idea is that each web over time, or each sort of string in the, or each sort of edge in the network is going to learn a weight. And basically the way you can think of this is, let's say that we have an example, an example, good things, right? And so we represent this in our network as 1, 0, 0. And then we have sort of our different weights. And they're all connected in a dense way. I'm going to just draw it like this to sort of, illustrate that this is the same thing. And as we pass these values through the network, the numbers get transformed and changed by the weights, by these edges. So you might think that this 1 will get multiplied by some value as it goes into all of these different nodes, right? And so now maybe, so for example, like, let's look at this node right here. Let's look at this node. This node will take all of the different inputs. So we're going to sum over all the different inputs. There's 3 inputs, so 3. And it's going to multiply it by its associated weight, right? And so that weight is going to be the weight coming from that example going to the first node. And that's going to be sort of the value of that node after when this example is passed through. So all 3 examples, 1, 0, and 0, are multiplied by each of their weights, this weight, and this weight. 1i represents here like the 1, 2, and the 3, as they sort of go in to represent this example. And so now this new node holds some value. And the other thing we can do, so this is linear, right? This is like a linear perceptron. The other thing we can do here is add some activation function. You can add some activation function, and that takes whatever value we get from that dot product and then transforms it in some non-linear way. And once we look at like some concrete examples of this, we can start to talk more about what some examples of activation functions might look like. So this process continues. It will happen for each of these nodes, right? This node's going to get a value. 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 And then the same process repeats for the next example. And so, for example, we'll take this node. We'll say we have some activation function on it. That node's going to be equal to the sum total of these five nodes, and they're going to have some value that's based off of, you know, whatever they were before. I guess we can say, instead of, maybe I'll say this is layer 1, this is layer 2, this is layer 3. So it's going to be, you know, xi for the second layer. This notation is clear. Dotted with the weight from that example going to the first example in. So let's say, I know this is kind of like wild notation, but bear with me. Let's say that these are the weights from the first layer. These are the weights from the second layer. And, you know, this is going to be equal to, this is not a 0. This is a, like the node. The same thing's here true. Right. So this makes sense at each stage. Sort of the information is being passed through the network, but it's being passed through as a function of all the different inputs and all the different layers that go across. And so this continues until the last stage, where we get sort of an example of what we got in the previous one, where we classify either as a 1 or a 0. Okay. So that's an example of a sort of a neural network in its sort of most basic example. Sort of more formally, I guess, to sort of like put single layer perceptron. So more formally, I guess, if we have sort of m of these of these input neurons for any one layer, right? This is any layer. We have n output. Input,
Confused,
output. We'll have some, you know, output yi, where we do some activation function. We sum across all the inputs from, you know, maybe I'll use so like a JE1, and we, you know, dot from the input to, from the output to the input, multiplied by the input, plus, and we can also have what's called a bias term. So each different actual node, so this is like, let's say this is, you know, yi. Each specific node can have what's called bias, which is just like a, you know, a fixed term that we add onto it. And we can also, I guess we can say here, this is a little bit clunky notation. We can also represent this in vector notation. So we might have some weight matrix that's sort of, you know, the size, like this would be m times n. And we can transpose this, multiply it by some, you know, input matrix as well. We need to know a deeper understanding such as backprop. That's a good question. I think that, like, you kind of need to know both, right? You need to have an intuitive understanding of how information passes through the network, as well as like how backprop might work. So we'll go through an example of backprop as well. But I think that this is a probably, I would say, like this would be the level of information that you need for the final. And we have some, and I'll upload these slides as well. Okay, yeah, hopefully that's helpful. And so, for example, like this function, you know, f, this function activation function will be applied element wise to like each example. So. Let's see, k by k, this will be k1. So this is the idea of a single layer perceptron. There are some limitations to the perceptron though. So, you know, for example, we can only learn functions that are linearly separable. So for example, if a function like XOR does not work. And so that's a sort of a limitation, right, of this example. And so the idea here is that we want to use multiple layers in order to sort of deal with this problem. But not only multiple layers, we also want to add a nonlinear activation function. And so the nonlinear activation function, which can be applied element-wise towards any output, is what sort of gives us the power to, do things like implement XOR or other nonlinear functions. And this is sort of the idea. And so when we look at a multi-layer perceptron, we'll take, for example, let's say we have X is like a, our input, and we have, hidden layer 1, hidden layer 2, all the way to hidden layer N, and then some Y, which is just a single node. And we might have, some number of nodes here, some number of nodes here, some number of nodes here, and, they're all kind of feeding into each other. We can sort of represent that as like, the first hidden state is going to be some activation function applied to the weights from the first layer multiplied by the input at X plus some, bias for the first layer. And this is going to be the same thing. So for example, like the second hidden layer is going to be some activation function. Now the weights that we're going to use are from W2. Now this X is going to be H1 instead. Does that make sense? Because we're passing the data not from X, but from H1, plus some new bias term that is unique to the biases there. And this will continue on until we have our Y. This will be, I guess, N plus 1 multiplied by the H n plus bias. Okay. So this is, I think, like a pretty good sort of demonstration of like what a neural network is. And I think now we're going to cover activation functions and loss functions. And someone raised their hand, so feel free to ask a question.
Yeah, like the professor in class,
I can't hear you. I don't know why.
Can you hear me?
Sorry, give me a second. I don't know why I can't hear you.
Okay.
Nicholas, if I'm saying your name right, I can't hear you. If you have a question.
Can you hear me now? Can you hear me now?
I still can't hear you. You can type. Oh, that's totally fine. That's totally fine. I'm gonna also mute the guy whose mic is on, which I now realize. No, you can speak now. I think I can hear you if you talk.
Yeah. So I guess like my question was like with regards to like the number of nodes in like dense layers. Like how do you know like how many you need? Like is there like a way to like if it's specific problems you need a specific amount of layers? Like how do you quantify that? Yeah.
No, that's a good question. There's not like sort of a there's not like a golden bullet on like how many layers you might need at any given point. So there's a few things that you might want to think about, like, for example, having a lot of layers or having a lot of nodes per layer is more computationally expensive, right? Because you're going to have to, do a lot more calculations at any given time, but you are able to sort of like more richly represent the data. And so I guess my rule of thumb would be you want to have enough nodes to which you can like accurately represent your data, but not like so many nodes to which you're overfitting. And so, for example, like if I have, 30 features that I'm working with in an example, I'm not going to want to have a network that has more than 30 nodes per layer because it's just going to overfit on every single possible feature. Rather, I want to have a small number of nodes that can sort of accurately represent what I think might be, the number of dimensions along which a node like data might be split. So for instance, like if I have, like 30 nodes and I think, maybe there's like 5 big components that I'm trying to learn here, I might use 5 nodes. I might vary it in between different layers. I might, there's something called a variational autoencoder, which is basically the idea of squeezing everything down into a single node. And whatever that single node is able to represent is like a representation of like the bigger network. And so I think it depends on the uses. That's makes sense.
Yeah. I guess like is that something that you think is like examinable, like having that sort of intuition, or like I guess it's not really something we covered like in class so much.
No, no, I don't think it will be, because like this is one of those things that's like, the thing about neural networks is a lot of it is very like experimental. There's never really like one correct way of doing things. So you're not really, I don't think you're going to be asked like, what is a good number of layers to use. You might have like maybe some example, maybe you'll have like an example that's like a chunk of code from like TensorFlow, and it might ask you like, how many layers are being used here, or like how do I represent the number of layers? How many like weights are there? If you have like for example, if I have a densely connected network
Mhm.
of n inputs and m outputs, how many trainable parameters are there in the network, right? And so then you have to figure
Okay.
out like how many different edges are there between those in the densely connected network. If it's not densely connected, how is it connected, and what does that mean for the number of edges in the graph? That's, I think, more kind of question that you'll get on the exam.
Okay. Okay. Sure. And did you take the class with Yassine, just out of curiosity?
I did take the class with Yassine, yes.
Okay. Okay. All right. Great. Thanks. Yeah.
Um, okay. So you see these functions f that are in our example. This is what's called an activation function. Now, I'm not going to spend too much time on this because it's not really, I think, very difficult to learn on your own. But the idea here is basically, if we want to, we basically can represent any linear function without the f's. When we introduce the f's, we can start to represent nonlinear, functions. So for example, like let's say we want to, classify XOR, right? There's no linear, you can't draw like a linear function to change the two, but we can draw, maybe some nonlinear function. And so this is where activations come in, and there are a few famous ones. For example, we might be interested in tanh, which takes your data from R and puts it into -1, +1. So it looks like something like this. This is +1, this is -1, this is negative infinity, positive infinity. Another common one is ReLU, which takes your data from R and puts it into basically a D negative. It basically removes negatives from your data. And so like if you have any negative number, if I have any negative number, it'll just zero it out. And then whatever my positive numbers are, it'll continue to do that, right? So if this is 5, this will be 5. Basically, it just takes away the negative. The last one I think I want to do is the sigmoid function. Sigmoid is actually pretty useful because, and it's usually represented using a sigma. It takes the data and squeezes it from -infinity, +infinity, or real numbers to 0 and 1. So if I was to draw it, it would look something like this. And the nice thing about this one is that you can use this one for probability, right? You can basically use this sigmoid as like a way of converting your previous nodes into some probability measure. And so, like for example, would it be good to memorize? I think it's good to memorize the activation functions. I mean, these are the 3 that I would say to memorize. So actually, there's one more you should memorize, but I'll cover it in like right after I talk. I think it would. But it's like I don't think it's that costly of a thing to do. So the third one is called softmax, and softmax basically takes it's a little bit like sigmoid, but basically what it does is it basically converts your data into a probability distribution, into a valid probability distribution. And so the equation for it is the exponential, let's say like xi divided by the sum of the exponentials for, I guess, xj. And so this is like, if I have a node x, let's say I have like 3, let's say I'm coming in from, let's say I want to have a valid probability distribution over a vocabulary of 3, or like, vocabulary is not good. let's say that I want to do, let's say I want to do a valid probability distribution over positive or negative sentiment. I take for each of these xi's, I will basically sum across all of the different inputs that come in xj and basically create like a valid probability distribution over that, if that makes sense. So this is the 4 activation functions I think are most useful to learn. Softmax takes, it's probably the most useful one that you'd probably use like in the real world setting, to take like, you know, a set of nodes in your previous layer and put them into the next layer in a valid probability distribution. The next sort of component, so the next thing I want to talk about is sort of back propagation. And so in our previous sort of talk, in the last little bit of time, we talked a little bit about how, you know, we have these weights, and these weights are really the bread and butter of how we turn our data into predictions, right? Because we multiply the data by these different weights in order to sort of transform that data into values that we can then use to sort of classify data. But the big question remains, like, how do we learn these weights? How do we learn the weights? So so maybe before I ask about how do I learn the weights, we can sort of think about what the like story of a neural network is. So we have like an example or a set of examples. We have a neural network. We pass, and let's say we have some training examples and some testing examples, right? We'll first want to pass our training examples through the neural network, right? So in order to get predictions. And the idea is if the weights in this neural network are correct, these predictions would be correct, right? And so in the forward pass, we pass our examples through the neural network. And not only do we make predictions, but we actually, since we have the predictions and we have the, you know, true answer, right? We have the predictions and the gold labels. We can use that to calculate a loss function. Okay. And the loss, I say we should use a loss function to calculate the loss. And so we're able to generate this value called the loss. And the loss is kind of what it sounds like. The loss is a measure of how wrong we are in terms of our prediction. It's so, for example, if we predict that the label is 1 and the, you know, gold value is 1, our loss is 0 because we predicted correctly. But if we predict that our label is 0 when our you know, gold label is actually 1, then our loss is, you know, 1, for example, because we were incorrect. So that's what the forward pass is. That's when we take data and pass it through the neural network in order to get a prediction, and we can sort of compare that to the gold label in order to see how wrong we were. In the back propagation or backwards pass, this is the opportunity for us to actually learn the weights in the network to train the neural network. And so we use this backwards pass. We use this loss function or this loss value to perform what's called back propagation. And back propagation is when we take a loss value and we tweak the weights in the network a little bit so that in theory, the loss gets reduced. And so the idea here is if the loss function is like a description of like how wrong we are, if we're able to tweak our weights in the neural network to reduce the loss, to bring our weights closer to the real answer for that example, we basically learn the weights that generalize best over the entire network. So we perform back prop, we learn the weights for the entire network. And this is the idea of forward and backward pass. So let me think about what I want to do here. So an example of a loss function. Let me find an example of a loss function. I have a question about how you wrote softmax. Yeah, go ahead and ask that question.
Yeah, so for the way that you wrote it down, like essentially that like the xi, that's like after you've done like the dot product with the weights and then added the bias, right? Like for each,
Yes,
that's
yeah,
correct. Okay. All right.
yeah, yeah. It was a
That's for
little bit rough. Yeah.
each node. So like the whole, like all the nodes like in totality would represent a probability distribution, like that add up to
Yes,
one.
exactly right. So like yeah, so like when you sum over J is the output, the number of output nodes, and the xi is like that output node. So let's say that there's J out, there's say that there's like M output nodes and you're at output node I. This is what you do, like, so xi is like after we after we apply like the weights and the bias from that layer. That's how we activate it.
Okay, yeah, thanks. Yeah.
The activation function takes place after
Sure.
we do the weights and the bias.
Yeah, makes sense. Thanks.
I'm looking for, let me look for a simple loss function. To kind of give it. Okay. So for a good example of loss function. So this is, let's call this the back propagation. A good example of a loss function is a mean squared error. A mean squared error is like a very simple, like for example, we might take, let's say we have n training examples. For each of those examples, we basically want to tell us, given our prediction for I, how wrong is that given the gold label? And we'll square it because we don't want, for example, I draw like, let's say this is our predicted function. We don't want it to be like negative or positive depending on what side of the function it's on. We just sort of want a representation of like how basically how big are the errors that our network generates. And this is like kind of a funky way of doing it, but like if you get the idea of like, we want to figure out like what are the errors that come up for each of our examples, and that's sort of what we do here. Okay, so back to backprop. We might have what's called, so the point of backpropagation is really to optimize the network parameters. So let's say we like want to learn parameters theta by minimizing the loss function with respect to theta. So if we call this the loss function, we can sort of say, what's the loss function given theta? And I know this isn't represented in theta, but like you'd think that like theta is tucked away in here, right? Because the way that we get the predictions is using theta. Okay. So the predictions are tucked away, like the theta is tucked away in the predictions. The theta can be, maybe this is our like all of our weights from like 1 to n. Okay. If we have n layers, maybe I should use k layers. And so what we do in sort of maybe like an example of like what a back propagation algorithm for optimizing the network is a stochastic gradient descent. So what's gradient descent? So I think the best way to sort of think about this is like to think about the three different words separately. So first, I guess, like what is a gradient? A gradient is, if you remember from calculus, is sort of this idea of like, if we have a ton of different variables, how do we take the derivatives with respect to all of those different variables? Descent is, we want to, using those sort of like, using sort of those like, how do I say this? Okay, so imagine this. Imagine that we have sort of this, n-dimensional space, or I guess I'll say like we just have like a, some n-dimensional space, and the n dimensions represent the different parameters in our network. And as we change each parameter, the loss of the model changes, right? Because let's say we take like a specific, let's say this is like one direction of our so this is one weight. If we change the weight, the loss of the model may go up or go down, depending on what changing that weight does to the performance of the model on our model. What we want to do is we want to find the lowest point in this loss landscape. You can imagine this n-dimensional space as a landscape of valleys and of mountains that represent, given at any point in that landscape, what the sort of loss is, right? And so, for example, at this point in our landscape, we might have, parameters in some setting, and this is the loss that we have. And we want to find, what is the lowest point? What is the lowest point in our loss landscape? Because if we sort of minimize the loss on the training set, that is probably going to give us a pretty good representation of the data to use on training, on the test set. And so the gradient is this sort of idea of the derivative of a function with respect to all of the different variables, whatever those different variables might be. It's descent because we want to basically travel down the mountain and find the lowest spot in the loss landscape, because having the smallest loss, having a loss that's the smallest possible loss is probably going to be a pretty good network for new examples that we might want to introduce into the network. And it's stochastic because in the loss landscape, it's very easy to get stuck in different valleys and different mountains. And like you might overshoot the lowest point of the map, you might undershoot it. And so we use stochasticity to basically take little steps, baby steps towards the lowest point in our loss landscape, or the lowest point that we can find, the global minima, hopefully. And so what this sort of algorithm looks like is we want to randomly, I spelled randomly correct, randomly initialize the weights theta. And then for each epoch, maybe we have k epochs, we want to shuffle, first we want to shuffle the data set. And so we'll represent the data as X and Y. And we want to shuffle them. Maybe we have n examples. That sounds fine. Yeah, we have n examples, shuffle. Shuffle. And then we want to, like, for each example, for I in n, we want to update the parameters. And so the way we update the parameters is basically, and I'm going to actually write this on a different page because we're starting to run out of room. For each time, we're going to want to take the derivative of the loss function for that example I with respect to the parameters of the network. And then this is a learning rate. This is a small number, maybe it's 0.001 or something, that we multiply by this gradient, by the loss function. And we basically change all of the different parameters in the network in order to sort of get a better idea of all those different things. So please talk about the difference between epochs, iterations, batch size, those sorts of things. I'm happy to do that. So does what I've written so far make sense before I jump into those concepts? Like this idea that, like, I have this function and I'm, calculating that I have this loss function and I'm calculating sort of the derivative of the loss with respect to the parameters and then, going down. Does that part make sense? Okay. So I think let's talk about epochs. I think iteration might be the same thing as an epic, but basically the idea is this. If we do this once for all of our different examples, we're probably not going to learn a ton, right? It's like kind of thinking about like, if you're going to teach someone an exam, like how to do a math problem, you probably want to give them multiple different examples of the different math problems in order to kind of build better intuition over time. And so what an epic is it's basically one epic is one instance of showing a model all of our training examples. So let's say we have 50 examples in our data set. One epic is the process of training the model on all of those different 50 examples. If we have multiple epics, we show the model those examples that number of times. So for example, if I have 10 epics and I have 50 examples, I will show each of those 50 examples 10 times for a total of 500 different training iterations, we can say. So an iteration might be one example going through the network, whereas an epic is every example going through the network, and we're going to have multiple epics. So we're going to have every single example go through the network multiple times. A batch size is more of a sort of an engineering thing that was created because, pushing through, especially because we have the ability to use matrices in an efficient way, pushing in one example at a time through a neural network is not the most efficient way of doing it, right? Because if you're just going to push through one example at a time and calculate one loss function at a time and backpropagate once at a time, first of all, it's not very computationally efficient to do that, especially if we have the tools of like matrix calculus. Second of all, it actually can be a little bit dangerous to do that because if we're going to update the weights with respect to only one example, it could be that example is an outlier or that example is not representative of, great, big, like more generic patterns in the data. And so what we use is a batch size to basically say, instead of putting through one example at a time, let's put through, the batch size number of examples through the network at a time. Let's put through 10 examples through the network at a time. And then we calculate the loss basically as an average of those 10 different examples and how they did through the network, and then update the layers as an average of those 10 different examples. And so, for example, let's say we have 10 epics, we have 50 examples, and we have our batch size is 25. How many different times do we pass our data through the network to update layers? So one iteration, train on one batch and backpropagate. Yeah, let's call an iteration that exactly. It's one example or set of examples goes through the neural network to get a loss, and then we use that loss back through the neural network to do backpropagation, update the weights. This is forward pass. So if I have, these, how many iterations do I have? Yes, exactly. 20 times. Yep, exactly right. And so, yeah, this is just a little bit of like, so I have 20 iterations. And yeah, I think I'll leave it at here with this discussion of epics. But this is exactly right. So let's do it's kind of a complicated example. Okay, so let's do maybe an example of a backpropagation forward pass. Yep, okay, that's what I want to do. So now let's actually, look at what does backpropagation really look like. So it's sort of a two-step process. First we have the forward pass where we compute the loss for, some given example I. With parameters theta. And then in the backward pass, we, we propagate the gradient of the loss backwards through the network. The gradient of the loss, and this is basically like the derivative of the loss with respect to the thing. This is the same. The derivative, I think I actually want to write it like this, the derivative of the loss. The gradient of the loss, propagate it back through the network. So use gradient back through to update data. And so let's say our network is just a simple network where we have two examples and they feed into something like A. And there's like weights 1, weights 2, bias, and this goes to some output that we can then output, or I'll say prediction actually. Prediction, and then there's the loss that gets created here. So our network is pretty simple. We just have sort of two nodes. We have weight 1 dotted with x1 plus, weight 2 dotted with x2 plus the bias. And then our prediction is going to be activation function. So let's use the sigmoid activation function on A, which is equivalent of sort of saying, actually, what did I write for sigmoid? I didn't write anything. The sigmoid is going to be actually not gonna. Yeah, I don't think I'm gonna write the sigmoid function itself. I guess what I can say is the sigmoid is going to be equal to the probability of like y being equal to 1 given x and the weights, the bias. Okay. And this is going to be 0. Okay. And we can also have sort of our loss function, which is just we're going to divide by the number of examples, and then our loss function can be sort of iterating over those examples. What's the normal, what's the natural log of sort of the probability of our true given our initial. And so, for example, we might have our data might be x1, y1, and then we have another example x2, y2, where x's are in R and y's are maybe like y1 is 1 and then y2 is 0. So the y's in general are in y1. Do we have to do a forward pass before doing a backward pass? Yeah, you have to do a forward pass before doing a backwards pass because you use the loss function. You use the loss that you calculate in the forward pass in the backwards pass. So this is our network. I'm going to just go ahead and copy this and make it smaller on the next page, but this is sort of like what we're working with for our examples. Oh, I don't need to do that. So paste this and I'll make it smaller. Put it over in the corner. And so now I guess now we do the forward pass. So first we want to calculate for the different examples, for example 1 and example 2, what our prediction is. So first we want to calculate A being sort of the weight times the x1 for the first example plus weight 2 dotted with x2 for the first example plus the bias. And then for the output, we want to go ahead and just take the, sigmoid activation function of that A1, which is itself going to be basically the probability of y being equal to 1 for that example x1. Should loss be negative sum by I? No, I don't think it has to be multiplying by the actual by the actual thing, because if it is 0, I think it still works. I mean, this is just a toy example. But I think that if you multiply, if you just take the log of, maybe the log of 0 is undefined though. Oh, but this is a probability. Log of 0 is undefined. Yeah. So I don't think that's a problem because we're not actually using like if it was just 1 or 0, it would be the case, but like because it's a probability, it's okay that we don't multiply it by yi. Okay, so we do this for both, examples, and so this is going to be like A2 and O2 is going to be pretty much the same thing, but just instead of like x2, it's going to be x1, and then this is going to be like the activation on A2, if this makes sense so far. And so this is the first step in sort of getting our predictions. And I'm going to change this to pred because I said I was going to do that. Okay, now now we have the opportunity of sort of figuring out what our loss function is. And so our loss is going to be equal to sort of 1 divided by the number of examples, and then the log of, I think I did this, it'll be like the log of what is the label given x1 plus the log of, what's the probability of getting y2 given. And the reason this works is because y1 is equal to 1, and then y0 is equal to, or y2 is equal to 0. And so like basically, this component's going to be for the 1s, and this component's going to be for the 0s. And so both of the different possible labels are sort of being accounted here. And this is actually going to be 1 divided by -1/2 multiplied by the natural log of the prediction for the first plus the natural log. And instead of the prediction for the first, it's actually going 1 minus the prediction for the second, because since it's 0, we have to reverse it in order to get it to be in the right magnitude, right? Because we want it to be negative, or we want it to be positive actually, because the leading term is negative. We want like these two, we want this term to be positive, and we want this term to be positive because it's multiplied by a negative term. And so this is sort of the idea here. So this is the, does anyone have any questions about the forward pass? Okay, I'll take silence as.
Yeah, I had a question.
Go ahead.
Yeah, so like I'm still a little bit confused. So this is like something to do with entropy. What is this loss function called, festival? This one that you wrote down?
This loss function is going to be like it's going to be like it's like cross entropy loss is the idea.
Okay. So then like where does the
I just kind of wrote it, like it's like a cross entropy loss. Like this is, I think, what the way we would describe it.
Where does like the gold label come into it? Because that's what I'm sort of not seeing.
Oh, these are the gold labels.
Okay, those are the ones. Okay, I see.
So because like the way that you see it written, it doesn't actually include the gold label, but the way that we sort of write it takes that into account, right? Because like here we take the natural log of the prediction, which is like sigmoid over the A. So this is going to be like the probability of y equal to 1. And then like
Okay.
this is sort of the same thing, right? But we're doing 1 minus the prediction because this is going to be like probability of y equals 1 given x2. But we actually are interested in, what's the probability of y equals 0 given x2, right? Because we know that this is the x2, because we know that y2 label is 0. And so we just do 1 minus that in order to get.
I see. I see. Okay. 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 Thanks. Yeah.
Haojin, I don't understand is your question like what does cross entropy mean?
No, no, I just referred to it as this is the last function, so I just
I, your microphone is like kind of broken, so maybe it's best if you type your question because I couldn't really understand you. Just try to answer question. Okay, I don't know. Okay, let me know if you, oh, he was answering your question. Okay, all right. Yes. Okay. So does this, okay, I think this hopefully makes sense. So now basically the idea is that have gotten some value, a loss value that we can now use to update the parameters in our network, namely update the beta, W2, W1. So now we do, so now we like basically use this loss to update these parameters. That makes sense. So backward pass. So, as like a refresher, I don't know if I can still paste this? Great. Okay. So we have 3 parameters, right? We have W1, W2, and beta. And so we have to calculate, first we have to calculate what's the derivative of the loss with respect to W1, what's the derivative of the loss with respect to W2, what's the derivative of the loss with respect to beta. Okay. So, this is all, I think, kind of long-winded, but like the idea basically is we take this loss function, which formally we define this way, over all the different examples that we have. What's the probability of sort of, yi getting the thing? But really, and I guess in theory, it's actually going to be 1/2 ln p y1 given x1 plus ln p y2 given x2. Okay. So we now want to take the derivative with respect to, these different weights. And so what we can do here is basically we can use the chain rule because this is really the bread and butter of back propagation. So I'm going to go ahead. I don't have much space. Let me just copy. So I have the derivative of the loss. I'm going to just do weight 1 because all the examples are going to be the same as W1, just with different variables. So first we want to do the derivative of the loss with respect to weight 1. And so what this is going to be sort of equal to is, see how I want to write this. So what is loss? What is the loss really? The loss is basically the, see how I write this. So we take the derivative with respect to W1 of this function here in the before, right? So it's like ln p y1 given x1 plus ln p y2 given x2, right? What this really is going to be, ln of the prediction 1 plus ln of the prediction, or 1 minus the prediction 2, which we kind of covered here in talking about why this is the loss that we found. Okay, it's going to be, and because of the calculus rules, we can pull out this negative 1/2 in front. Take the derivative with respect to W1. And then this is sort of where the chain rule comes into play, because we want to say, okay, well, the derivative of ln with respect to the prediction, the derivative of ln pred 1 with respect to W1 is going to be the derivative of ln pred 1 with respect to pred 1 times the derivative of pred 1 with respect to the weight, right? Because the prediction depends on the weight. And the same thing is going to be true for the other side. And so, for example, the derivative of ln 1 minus the prediction 2 is going to be, we're actually going to want to take the derivative first of 1 minus the prediction 2, although you could do just take the derivative with respect to just the prediction, but that would be, how do we get ln 1 minus pred 2 in the second line? So if we go back to when we calculated the loss, if you look here, we know that the sigmoid gives us the probability of y equal 1 given x2. But our gold example is that y2 is equal to 0. So what we do is we take 1 minus the probability that y equals 1 given x2 to basically give us the probability of y equals 0 given x2. Okay. And so just sort of like unpacking this, we'll take the derivative of 1 minus pred 2 with respect to pred 2, and then the derivative of pred 2 with respect to W1. Okay. This is super messy. Let me write it a little bit neater. Respect to W1. Great. So this is basically the, so to sort of write it more neatly, we now have the derivative of the loss with respect to W1 is equal to, 1/2 multiplied 1/2 times this, which we can rewrite maybe a little bit nicer as the derivative of ln with respect to the prediction for 1 divided by the derivative of the prediction for 1 multiplied by the derivative of the prediction for 1 divided by the A node of the network, and then the A node of the network divided, and then the derivative of the the derivative of the A node in the network by W1 plus the derivative of ln 1 minus pred 2 divided by the derivative of 1 minus pred. And these ones are going to become x2 and x1, or I should say, hold on. These values are going to become Oh, why? Tempted to start an invalid broadcast session. Can people still see my iPad? For some reason, it says that it disconnected. Let me try something again. Why is this doing this? It was frozen for you. Okay. Okay, for some reason, my Zoom has just decided to just totally stop. Give me the exam be in our normal classroom. It should be, I'm not 100% sure, but like all that information will be like emailed to you by Professor Benajiba. You can't see it on SSOL. Yeah, it should be, it's on the syllabus. It's like 11 May at 7 p.m. Yeah. I don't know why this isn't working now. Give me just a second to try to like turn this off and back on again. Okay, I think we're back. Okay. So if we go back to the original network that we have, if you notice here, we have sort of like each example, X1 and X2, is really going to have like two separate inputs. We're going to have X1, X1, and then X1, 2, and X2, 1, and X2, 2. Do you guys see that, how it's like represented here as like the two X's, and like for each X, there's sort of two sub X's that represent the different features. In our back propagation, when we take the derivative with respect of derivative of A with respect to W1, we're going to get that first feature for the two examples that we have, if this makes sense. Okay. And the reason we're going to get the first feature is because this first weight corresponds to this first feature. That gives some intuition on that. And so, I mean, we can continue to sort of like, do all of this, calculus. And so, for example, our first term will get, 1 divided by the natural log, right? So you take the derivative of the natural log, you get 1 over whatever the derivative is. In this case, we'll just get so we're taking the derivative of something with respect to itself natural log. So it's just going to be sigmoid of A1 times, and then the derivative of the prediction with respect to A1 is going to be the derivative, it's going to be sigmoid. The derivative of the sigmoid function is equal to the sigmoid times 1 minus the sigmoid. That's like important to know. So we can just write it like this. And then we know this is x11. The feature 1 for the example 1. And the same thing is going to be sort of true for the next step. We're going to have 1 minus 1 over 1 minus the sigmoid, because we're just taking the derivative of the something with respect to itself in log. Taking the derivative of 1 minus the sigmoid with respect to the sigmoid, so we can just pull out a -1 here and then take the same derivative that we would otherwise. And then we have x2, 1. And then this can simplify further because this will cancel with that and that will cancel with this. And so we get as our final answer 1/2 of 1 minus sigmoid A1 multiplied by x11 plus, or I guess minus, minus sigmoid of A2 times x21. So basically, this is the derivative of the loss with respect to weight 1, and it's 1/2 1 minus sigmoid A2 A1 times x11 minus sigmoid of alpha 2 of A2 times x21. And so using this, we can then update weight 1. Basically, it's going to be equal to, use this just like set to W1, its original weight, minus some learning rate. This is a small number of whatever the derivative is. And then we can do the same thing for W2 and the B and the bias. And so, the trick here is basically we have, this derived by, but we have the loss with respect to some trainable parameter. And we basically use the chain rule to figure out, what is, the loss with respect to intermediate stuff, multiplied by the derivative of the intermediate stuff with respect to that parameter. And so whatever the chain rule ends up being is kind of up to you, because you might want to break it down further to make the derivatives easier, or you might want to, keep things tighter together so you don't have to do as many computations. But this is sort of the generic idea of the chain rule. And then once you figure out what this value actually is, you can then use it to update the parameter like so. So this is backpropagation. Does anyone have any questions before I move on to attention and self-attention? Okay, I'm going to move on to that as well, because I think that that would be good to do. So
I had a quick question.
yeah, go ahead.
So for the exam, for instance, like I feel like a lot of these computations might be like simplified through using like matrix and vector calculus, that like, like there's like rules that you sort of memorize for that sort of stuff. Like, is that something we would be given, or something we should know? Or like, yeah.
You will not have to do matrix calculus on the exam.
Okay.
You might have to do some like generic calculus like what we just did, but not matrix calculus. Any like, you're not going to have to like memorize complicated derivatives. You should know some things though, like, if the derivative of like some log, like log of x is equal to 1 over x, like that's kind of something that's like expected for you to know.
Right.
But I think anything more complicated than that would be given.
And then also another question, like with regards to like gradient descent, so like it's the function isn't necessarily like the objective function for the neural network is not necessarily convex, right? Like it could be concave, or it could be like, or it could be convex, or neither, right? Is that correct?
Yeah, and so that gets into some more like machine learning stuff about, what properties the function has, determines whether or not it might be possible to use stochastic gradient descent and guarantee a certain kind of solution. So like convex, like if you're optimizing like on a convex function using stochastic gradient descent, you can, guarantee that you're going to get a global minima. But
Right. Yeah, that's sort of my question. Like, as in, like, is that like important, or like, do we just like care about like getting like a decent local solution? I guess. Like,
I mean, in general, like in practice, you're gonna want to try to get like a decent local solution because you don't know whether, I mean, unless you know your function's going to be convex or not.
Yeah.
But usually in practice, like in natural language, it's very hard to know that for sure a priori.
right. Of course. Okay. Thanks.
How to solve backpropagation if our activation is ReLU. So the derivative, so basically like the derivative of ReLU is just going to be 1 in instances where x is greater than 0, and it's going to be undefined everywhere else. So 0 everywhere else. You just kind of zero out if it's an undefined derivative. Otherwise, the derivative of ReLU is just the input, or 1. I mean, piecewise activation. I mean, if you have a piecewise activation function, like you're not going to be able to, it's going to be kind of hard to write like a closed form solution, right? Because like the idea of these like closed form solutions is that we can sort of plug in our answer and then calculate the loss. If you're doing piecewise activation, you're going to have to represent functions in your loss function that then like translate to the different, possible values. But you just want to sort of like, I guess, figure out what the derivative is for any possible case, and then like give that derivative when that example is provided in the function. So you can represent that using a function. Yeah, no problem. Okay, so attention. So the problem that we kind of have that's hard to solve is like, how do we encode a sentence? And this is an important problem in natural language processing, because we want not to only understand the meaning of words, but also the meaning of sentences, phrases, and documents. And so we might use something like pooling a bunch of different word embeddings together. That might be good. Or using like an RNN and taking the last representation of the RNN and using that as a sort of representation of the sentence. But these are not really perfect solutions, because they're sort of like, they don't really weight the meaning of the different words depending on how important they are. And that's what attention helps us do. Attention, you can think, helps us pay attention to different parts of a sentence when we're encoding it. And so something, I guess, what we can call attention is basically a learned dynamic weighted average for words in a sentence, for encoding. Why is it learned? It's learned because we're going to use a neural network to learn it. Why is it dynamic? Because we're going to, learn different sets of attention at different points, depending on what the, inputs are and what the sets of words are that we're using. It's not always uniform. And it's weighted because different words are going to have different values that we take in order to like sort of weight the words. And so let me think about how I'm going to say this. And so how do we do this? We want to like basically calculate a score that basically captures how relevant each encoder state is to the current decoder state. Let me actually write like so let's say we have an encoder and a decoder, and we have this is the hidden state 1, hidden state 2, hidden state 3, hidden state 4, and we have a decoder start token y1, y2, y3. We pass it through some hidden state. This gives us y1, and then this goes down to y2, and so forth. Right. So, and then, this will be like, so this is the idea. Maybe this is like an encoder decoder architecture. So we basically want to, first calculate a score of sort of how relevant each encoder state is to the current decoder state. Or encoder state. So for example, let's we'll look at H2, for example. It's going to receive input from all of the, I didn't mean to erase. It's going to receive input from all of the different decoder states. And we want to figure out, how much value does each of the different, how much is the different things value. Normalize these scores using softmax to basically create like a valid probability distribution over the weights that are coming into a decoder state. And then we can calculate our context vector using a weighted average of these encoder states, and then calculate the actual vector using these weighted encoder states. And so how do we, calculate the scores? We might want to use some function that compares, we're at a decoder state I-1, and we're looking at an encoder state J. And so we want to do this for all of the states up to I-1, J is equal to 0. So like, oh, actually I already used J. Maybe I'll say K. So in this instance, we have like, encoder state J up to I-1. We have some encoder state K. And all of these are feeding into, this, I should write it like this. All of these hidden states are feeding into this hidden state. And we can just calculate this using maybe like a dot product to see how similar the encoder state is with the decoder state. And then what we want to do is we want to just basically calculate like a softmax for, all of these different, all these different edges, right? Softmax this. So the way we do that is we just sort of like take this score function that we had before. I guess we used dot product, but I'll just write score actually so that it's more generic. HDJ, HEK. And we do this for all from J equals 1 to I-1, right? And this softmax is just going to be like for each specific J, it's going to be like see, J equals 1, I-1, you're going to have the X. XJD. And this is going to be like a specific J, a specific J. This is how we calculate the, the scores. These are the scores. This is sort of like the weighted average part of the attention. And then we calculate the context. And the context CI is basically the bread and butter of like what our state's going to be at the end of the day. So like, summing over all of the different J's, we're going to have some score that multiplies by the encoder state that we multiply with the encoder state to basically get the context. And this context is fed in. This context is fed in to the encoder state. So we have this context I that we then feed into the encoder state. Or sorry. I think I flipped some of the E's and the D's, but in any case, what it will be is basically like the context is on the encoder states, and then we feed the context into the decoder state. Encoder, right? Decoder. And so the idea is like the context we use to basically squish all of the encodings together to get a weighted average encoding state that is weighted across all of the different encoding states that we've seen so far. And then we pass that context into the decoder state along with maybe, you know, the previous answer, right? And then that helps us create our new, this is super, hold on, let me just kind of like rewrite this in a different page. So calculate scores. So we have our, you know, x1 to xn. These are h1 encoding states to x to hn encoding states. And this is all going to be passed into some context I. And let's say that we're at yi. Yi is going to take from the previous state yi minus 1, and it's going to be a decoder state I, and it's going to be, you know, making a yi I plus 1. And so this context is going to be used to flavor up the decoder state. And the way that this context gets created is we take basically these scores using the softmax of the score. And I'm going to just copy and paste this because we've already written it. And this is pretty much the idea. Copy. And this is not, I know it says IJ. It's kind of a bad notation on my part because it really should be JK, KJ. This is the score. And then using the score, we have the context at step I. Actually, I'm going to use I because what I can do is just change where I say K to be I. And I'll take this and become N. Okay. Yep. So the context I is then going to be equal to the different score at every different stage times the encoder state J that we're, you know, that we're at. And then this is going to be fed to, this should be summed over. I don't know if I did it here. If I did, this should be summed over all the different J's. So basically this gives us like a weighted context, which we then feed into the model or the decoder state to create the next state. Does this make sense?
What's the meaning of alpha in this, in the context?
Alpha is basically a weight that we assign to each different decoder. Sorry, alpha is a weight that we assign to each encoder state based on how, I guess, informative that encoder state is in generating the output at that decoder state.
So never mind. I mistook your softmax output for a D. I don't know why. Sorry about that.
Okay, but it's clear.
Yeah, it's clear.
Okay. Okay, so yeah, does anyone have questions about this so far?
Can you clarify the last part? Like what you said, the context is then fed back to the decoder.
Sure. So in the decoder, so do you see this part of the diagram up here?
Yeah.
Okay, so we have this decoder state HJD, right? This is used to generate some output y I plus 1, right? And like before, we were basically just saying like, you know, I guess you could apply, you know, some function to HJD, and then that would give you yi1. And that function would be like HJD is dependent on yi. right? Now what we're saying is we want HJD not only to depend on yi, but also to depend on context I, which we now find using this thing.
Okay.
So maybe I should actually write this instead of just using a laser pointer. So we have some function, and that's going to be taking the decoder state HJD to create y plus I, y plus 1. And then before that function really secretly depended on yi to create yi plus 1. Now it's going to take not only the yi, but also the ci. And this ci is the weighted code. And actually, I should say before, it would not depend not only on, it would also, oh, okay, this is correct. This is actually correct. This yi, in turn, in the past would depend on like the last hidden state of the encoder, for example. So like y1 would depend on the encoder. So, but this is correct. This is like basically the idea. And so this basically helps us, create some interpretability in what parts of the encoding influence what gets decoded. And so you can think about, something like machine translation, where, the word order in your target language might be different than the word order in your origin language. So for example, you might think that in French, you list the adjective after the word, whereas in English, you list it before the word. And so, for example, a blue dog would be un chien bleu, right? A dog blue would be the translation in French. But if you were using like this mechanism where you were like taking all the different contexts and then weighting them, when you were at the position of decoding chien, which is the word for dog, you might have blue dog and then chien bleu, but it would learn that the second word corresponds to the first word and that the first word corresponds to the second word. And this is sort of the idea behind why we want to weight across the different attention weights. And so the encoding basically allows us to contextualize all of our outputs on all of our inputs. And we train them together. Yeah, I think this is what I wanted to say.
And is the score calculated differently apart from just dot product, or is there other things you can do? Or is that just generally what you do?
Yeah, you can do other things, but you usually want to do dot product. And I'm about to talk about an instance where, okay, so I'll answer your question in a second, because we're about to talk about self-attention where you do something a little bit differently. So hold that question, because I think we're going to answer it a little bit.
So in this context, like the loss is the score. Like that's how you train the network essentially. Like as in like that's what's like dictating like the changes. Is that like the correct way to think about this?
Well, the loss actually going to be like, the loss actually is what we're going to compare here. So like the loss will be some compare, and I think this is like a little bit like, so the loss is going to be like, something like taking the yi's and comparing them to like a golden yi or gold yi. So because the context influences the prediction, when we do back propagation, the context, these sorts of these context lines these like edges are going to be updated using back propagation, but they don't explicitly go into the loss function, because the loss function just explicitly takes the predictions of the models and the gold labels of the models. But in back propagation, because the predictions depend on the context, and the context depends on these scores, the scores themselves are trained during training.
Okay. All right. Thanks.
Yeah, no problem. So to kind of give another sort of way of thinking about attention is using queries, keys, and values. And so the idea here is like a query is going to be our current focus word. Like how similar is this query? How similar is everything else to our query? This is the query is what we're focusing on. You can think of it as like the like in the decoder state that we're at. The key is the representation of all the different words that we're comparing to the query. And then the value is sort of like the sort of output, the representation for the final output. So, you know, for example, I can write the query as like WQXI because it depends on the inputs. I think everything here will be like this. Where WK, where all the W's are going to be D by D. Oh. And then the score we can calculate as XI, XJ, which is going to be equal to dotting the query I with the key J. And then YI is going to be equal to taking the sum over all the alpha all J's, the value J from this 1 to J. So this is another way of just thinking about what we just been talking about. And I guess it's some different, like a different way of thinking about it, maybe with more of like a database feature in mind. But the idea is basically we have these weights, vectors, Q, K, and V that drive the extent to which our query is dotted with all of the different keys. And then those keys are sort of used to create these scores that then influence our values. And so you can think of this like creating like a mega value that is then used later on that's weighted using the scores, and the scores are weighted by how closely the query matches the key. So how closely does the current word, the focus word, the query match all the different keys, right? Based on that similarity score, we're going to weight the value to create like sort of a last value. Basically, self-attention, which I get to, I think I'll talk about self-attention now. The only difference between self-attention and regular attention is self-attention is, attention is what we looked at before, where we have an encoder state, and that's being used to create a context, then goes into the decoder state. Self-attention does not have this encoder to decoder, time step 1 to time step 2 encoding. What self-attention does is it actually weights all of the words in the same example. And so while you might think of, attention as you have sort of these, encoder states that create a context I that then get fed into a decoder state, J. Self-attention is instead all of the encoder states influence the value of all of the other encoder states. So basically there's like, and then these together, like you basically weight all of the states together in the same process to create some sort of, output representation that's weighted. So you can think like there's going to be a alpha 1. Let's say this. Let me rewrite this actually, because I think it's not clear. You have, encoder state 1, encoder state 2, so forth and so on. You want to multiply each of these by all of the different examples where this score is learned based on all of the different words basically you know, in the same example. It's not you're creating a context for later. You're basically learning alongside for each of these different examples what the weights are to then create some output representation, right? And so we can write this self-attention, we can write this as self-attention basically the same way that we write this here, this queries, keys, and values setting. So we'll have like our query, which is our, you know, output, our, you know, our weight matrix multiplied by our examples. Our keys are the key matrix multiplied by the examples, and then our values are the, you know, value matrix multiplied by the examples. Okay, so then this basically gets used to do some self-attention on the key value pairs, which in turn looks like the softmax. And so to answer your question before you're talking about using the dot product, what we want to do here is actually scale the dot product by the number of dimensions in order to basically stop the dot product from being arbitrarily large. And so we divide the dot, we basically divide the dot product of the queries and the keys by the number of dimensions to basically scale it from being too large. And then we, you know, again, multiply that by all the different values. This is a dot product. This is going to be just a single value. Or it's not going to be a dot product, I'm sorry. But basically, how do I say this? This inner product is going to give us a value for each of the different words in our self-attention sequence that we can then multiply by the actual values. So this is like, so this is going to be like our alpha, you know, ij, right? And this v is going to be our he j, right? And we're going to want to sum over, maybe sum over like all these different i's in order to get the representation for that specific word. Or maybe we don't want to sum over them and we just want to have, you know, d by d representations, a contextualized representation of each word in the context of all the different words. So from that, it kind of depends on what your use case is, but you can sort of have both examples. Okay. So this is attention and self-attention. This is a super complicated and difficult to understand concept. And so please ask any questions that you might have still. Yeah. Okay.
Wait, so for the self-attention, like you don't have a decoder at all. Like there was no decoder involved.
I mean, yeah, you don't have to have a decoder because the idea is basically that we're basically applying the mechanism of attention to weight our own sequences, right? Instead of using attention as a way of weighting stuff, weighting a different thing, we use attention to weight the current example. It's a little bit like you can think the word self implies that the attention is being applied to the place where the attention is being calculated, as opposed to regular attention, where the attention is being calculated for purposes of using it in a different area, in a different sequence, or at a different state. Here, the self-attention means that we're using the state, they're using the actual sequence to calculate attention and then weight itself. So self-attention is used for classification. Self-attention can be used for pretty much any natural language task. I mean, you can use it for machine translation, you can use it for classification, for regression, any task really. You can, you know, the whole idea behind something like BERT is you have a ton of these self-attention heads, one after the other, to create these very rich and robust representations of sequences that you can then do sequence classification on, you can do sequence regression on, you can do, you know, if you mess with the, you know, end of the thing, you can do translation or summarization or generation. So there's a lot of different applications to this. I think the most straightforward is probably classification, because you're creating representations and you can, you know, create linearly separable representations and then figure out like the sentiment of a word or sentiment of a sentence or something like that. But you know, it depends on like what you engineer on top of the system. Okay.
Do you have like any like resources you would recommend for like understanding self-attention in particular?
Yeah, I'll post a YouTube video that I think is pretty helpful in doing this on EdSTEM. I'll post it on the thread that I put for like the final review.
Okay, and then could you also just clarify like the alphas in this like in this situation, like how they're calculated?
Yeah. I mean, so the alpha. So,
Like what are we indexing over? Like I from 1 to n, like what is that?
Sure,
That's-
sure.
I think
So this is just like an example of if we wanted, the alpha is actually like, so I'm gonna remove them actually, because I think it's not super helpful. But like you see this softmax over here, this thing.
Yeah.
So this softmax part creates an alpha that is from 0 to 1. And it applies to every single word times all the different contexts. So in this case, it'll be like n times n basically, because like every encoder state is going to have a self-attention score from every other state. So like this is going to be HN, and then so like this is kind of maybe hopefully this isn't too hard to see, but like each of these arrows is like one alpha weight, right? What's the alpha from H1 to H1 or H2 to H1 or H3 to H1 or HN to H1? What is
Sure.
the alpha value for H1 to HN or H2 to HN or HN to HN? So the alpha, it gets created in the softmax of the n by n, and then we multiply it by v, which is basically our actual h's and our actual h's, to then actually create like a representation. And I'll post a resource for self-attention as well on EdSTEM. So we have a little bit of time. If anyone has any like unrelated questions that are not related to neural networks or backpropagation or attention, feel free to just put them in the chat or speak them out. We have a little bit.
No, also like I had a quick question with the
Oh yeah, go ahead.
The WQ, WK, WV, like how are those matrices calculated?
Those are learned parameters in the network.
Okay. So again, it's like similar, like you have some sort of like, I don't know, like then how do we construct the loss and everything? That's where I'm getting like pretty confused here. Yeah.
So the loss net, so this is all pre-loss. You can just think of WQ and WK and WV as parameters in a network, right?
Okay.
Just a ton of parameters in the network. And the loss is just calculated off of two things. What is the prediction of the network? And what is the gold label for that example, right? We take an example, we throw it through the network. This is true for all neural networks. This doesn't matter if you're using attention or not, whatever. Take an example, I push it through the network. That example has a gold value, okay? That example has a gold value. That example also has a prediction. Using the gold value and using the prediction from the network, we combine those two to calculate a value that's the loss value. How wrong is my prediction compared to the truth, right? I create a loss. Then I take that loss value and I take the derivative of that loss with respect to all of the parameters in the network, right? With respect to WQ, with respect to WK, with respect to WV, with respect to the biases, with respect to everything. Using that derivative, I then change the weight. I change the weight for WK marginally using that specific derivative. I change the weight for WV marginally using that respective derivative. And so the weights themselves are not part of the loss function. The loss function only will really consist of what's my prediction and what's the truth. Then when I take the loss function and I take the derivatives, that's when I'm able to compute the gradients in order to update the weights.
Yeah, I think that's fine. Like, I think I was getting confused as to like, you might need to do something special using loss because you're doing this sort of thing, but I don't think you need to. That
Nope.
makes sense.
Yep,
right.
exactly. Can I talk about ways of getting a representation of a sentence from words? All right, so Suchen, that is basically what I just did with attention and self-attention. So like this context CI is a way of getting a representation of a sentence from words, because we're basically, you know, summing over a bunch of different like representations of words in order to create a single representation of a sentence from a bunch of words. And in this case, attention is special because we weight all the different representations depending on how important they are. There are other examples of getting representations from a sentence that might be a little bit simpler. So for example, let's say we have word embedding. Let's say we have some word embeddings that are just static. So we have our embedding space. Let's say this is like 300 dimensions. And then we have our example, which is, let's say, n words. What we might want to do is we might want to do something called pooling, where we sum over each dimension to get a single representation. So this is a sum. We sum over each dimension to get a single representation for, and this is now a sentence, where the sentence is from W1 to Wn of 300 dimensions. So we can do something like sum pooling or mean pooling, where we take the mean instead of the sum. We can also use RNNs. And so, for example, like, you know, from our previous encoder decoder, we have X1 goes to H1, which then goes to Y1. And then this gets used to make another thing. And what we can do is take like this last representation as the representation of the sentence. So this is RNN. Can we talk about back propagation through time? We can talk about back propagation through time. Hold on, let me take a quick drink of water. So let me think about how I want to do that. So I'll just sort of give like a simple example of backprop through time. But the idea is actually really just the same as we were looking at in other examples, like with like taking the chain rule, right? Because like, let's say we have you know, X1, X2, X3, and then this creates like an H1, H2, H3, and then these you know, H's feed into each other. And then this H is used for, you know, some prediction. Then we have our roll label, and then we create a loss. Does this network make sense? It's like a backprop through time network, where these are like time steps. This is like maybe the dog barks. I mean, basically the idea is like, you know, when we take the derivative of the loss, this is like such bad, the derivative of the loss with respect to, you know, like theta h, or these are all like theta h. We can basically do is just like take the derivative of the loss and then say, okay, well, this is going to be the derivative of the loss with respect to whatever the prediction is, right? And then the derivative of the prediction with respect to the time step 3, and then the derivative of this time step 3 with respect to the derivative with respect to dh. And then we can do this for all of the different things, the derivative pred with respect to h minus h2, and then dh2 respect to dh. Yeah. So, and then this is going to be the same thing for like, if this is h, then we can say this is going to be x, and then we just replace the same thing there, and then you want to like work it out. And so the idea here is that basically we just want to like compute the backward pass through like, but you have 2 gradients for now. Yeah, and so what you want to do is, you know, compute the backward pass through the full sequence to get the gradient. So let me write it. Should we sum them? Yeah, like there's actually, I mean, like technically there's actually like several different strategies. Like you don't necessarily have to sum them. But like what you can do that. Like, so for one example of like what you might want to do is like, I would say multiply them. Honestly, like you might want to just basically take like, you know, let's say you have like t time steps. You want to basically compute like the loss with respect to, you know, d theta h. And so like you might take like the sum over like the, you know, dl and then d pred d h t, and then dht d theta h. Yeah, so something like this would be like what you want to do, where you just sort of like you basically sum them up. There are some problems with this with like vanishing and exploding gradients. Like if you're summing up all these different gradients, like if they're really large, you might explode them. If they're really small, you might like, if they might go to 0. So it's actually kind of an issue on how you train, how you backprop through time, because like it's very easy to like explode or vanish your gradients. And so you have to be a little bit careful about how you sum over all the different gradients, or how you like multiply across all the different time steps. But in general, you just want to sort of apply the chain rule to all your different. So actually this shouldn't be, this should be, the way I wrote this actually should be a product, because you want to multiply them. You don't want to add them together, because that's actually doesn't make sense. But like, this is how I would express that. Should be something. So you should not sum them. I don't know if that's an old message, but this is like how you'd want to do that for backprop through time.
Why does it not make sense to sum them? Like, let's just like multiply them.
You don't want to sum them because like you're basically kind of biasing the values to go up, you know, like if you're summing them, like there's no way for it to go back down. And so like, let's say that the loss on, first of all, like the thing about it is like the whole point of backpropagation is that you're taking the derivative and you're using the chain rule, right? And like,
Right.
so if there were basically like 2 branches of a neural network, you'd want to sum over them, like what we did in the first example, where there's sort of like 2 sections of the loss function, where one is for like label 1 and one is for label 0, that kind of stuff you want to sum together. But if you're backpropping through a network, you want to basically use the chain rule to figure out what is the dependence of this parameter on all of the different edges going up to the loss function. And so in this case, because the parameter depends on multiple edges that are interrelated, you still want to multiply them together because they're all part of the same network that goes up to the loss function.
Okay.
Are there practice exams or problems for this class? I don't think there are. Like, I'm sorry that I can't release the like solutions for the midterm. I don't have permission from the professor to do that. And so you might want to just look and see like what you missed on Gradescope and then like work the problems again. Practice exam problems are going to look like what they did kind of for the midterm, but I'll ask the professor to see if there's any resources that we can share with you guys. Does anyone have any like last minute questions before we wrap this up?
Yeah, like what would a question be like on neural nets and attention? Would it be mostly focused on the theory, since like we can't really work through, really can't work through a neural network problem like we can with the algorithms on the midterm?
Yeah, I mean, like, I think if you know what's on the slides for Benajiba's class, like you'll be good for the exam. I think that like, a multiple choice question is more likely to be theoretical, asking about properties of like, what are the properties of like linear activation, a nonlinear activation function, or talking about, what are the, how many iterations are there in this network, or what's the deal with like stochastic gradient descent. Whereas like a problem will ask you maybe to work out maybe like compute the attention weights in this example, and we'll give you like some words and some score, like some values to like run through attention score mechanisms to figure out like what the scores are for the weights. Or like maybe some classification task where like you have to manually classify examples using a simple like neural network that's already like partially trained. And then maybe we'll ask you like, what's the loss, and like what equation did you write to like update the parameters, but you won't have to do like any like really tedious calculus on the exam.
All right, yeah, and we'll see questions like that on the sample.
Yeah, I think
Percent.
so. I don't know if there's a sample exam or not, to be honest with you. I'm gonna ask the professor like what resources are available to be shared with students, because I'm not sure.
All right.
Yeah, I'm sorry I can't do more on that front, but yeah, it should be, I would just sort of look through. If you know the material on the slides and you get the sense of the format from the midterm, it's going to be pretty similar.
All right, thank you.
No problem. Okay, I think we're done unless anyone has any questions. Of course, like feel free to put stuff on EdSTEM if you have any questions before the exam. I don't see anyone else asking questions, so I think we're going to wrap this up. Oh, hello. Should we know how the mathematical computation forward pass for attention? Should we know the mathematical computation forward pass for attention? Yeah, I think you should know how to like calculate like attention scores for words. That would be good to know. No problem.
Yeah, so I noticed you didn't really talk about transformers that much. Are they going to be heavily covered on the exam?
I don't know if they're going to be heavily covered on the exam. I just didn't get to talk about transformers that much, but like a transformer is pretty simple. I think you can like, I think the extent to what a transformer is going to be covered is the extent that it's covered on the slides. And so
Yeah.
like thinking about, I don't know what he says about transformers, but I mean, basically you can think of them as like a lot of attention, self-attention heads stacked on top of each other.
Yeah, exactly. You can build it off of what was discussed here.
Yeah, I think that would be fine. Like, I don't, you're not really going to need to know a ton about like the inner workings of, I'm trying to see what he actually says about transformers. Let's see, attention, self-attention. Transformers and BERT. Yeah, I think I would just sort of read through the last PowerPoint, but like as you can like in other classes, like how much is the last lecture covered on the exam might be limited, and like if you go through the like PowerPoint, like you're not going to be covered, like nothing else is going to be covered that's more more difficult than what's like expressed there, which is pretty much what we covered here. And I don't think there's too much more to transformers. Okay. If there's no more questions, thanks everyone for coming to the Zoom. Good luck on the exam.
Thank you.
Yep. And let me know if there's any questions. Thanks so much.
All
everyone.
right.